Uh, okay, so everyone, a very warm welcome to this Siwalik webinar series. Today's speaker is Doug Burbank. Doug is working as a professor emeritus, University of California, Santa Barbara, California, USA. He'll be talking about late Cenozoic tectonics, climate, and deposition, Himalayan Intermontane and Foreland Basins. For those who are new to this series, I must include that Bob, Mukhtiar, and myself started this series as a result of inspiration from Bob's visit to Pakistan almost 2 years back. And in this series, we have already had 5 talks. This is actually the 6th talk of this series. The previous talks were by doctors, professors, Catherine Badgley, Hamad Ghani, Abdul Qayyum, Professor John Barry, Professor John Gary, and Professor Bob. Please visit the links that I have provided to retrieve these recordings for those who are new. Our next talk, which is scheduled on 31st March, will be by Muhammad Akbar Khan from Punjab University. So please stay tuned. I will now ask Bob to carry on the program. Bob, please.
Yeah, no, thank you very much, Irfan. And we're we want to be sure that we realize we're being hosted by the Geological Survey of Pakistan with Mukhtiar Khani, who's located in Quetta. And so through the good graces of the GSP, we're putting this program together. And next week is going to be, as mentioned, is going to be Muhammad Akbar Khan from Punjab University in Lahore, talking about paleontology. The following week is going to be Rajiv Patniak from Punjab University in New Delhi in India. And then it's going to be followed by Peter Clift, who's at Louisiana State University. And then we've got Andrew Miggs from the University of Oregon. And following that, at the end of April, is going to be Kay Berensmeyer. And I want to be especially grateful to our participants on the East Coast of the United States, for whom it's getting to be very late at night when they give their presentations, in part because of our daylight savings time. So, Catherine, thank you very much for being with us. Gary, thank you very much for being with us. We appreciate it. It's the middle of the night for you guys. I'm going to introduce Doug. Doug and I were classmates in the PhD program at Dartmouth College back in the tail end of the 1970s and the early 1980s. And I did my work in the Peshawar Plateau, in the Jhelum area, and Doug was following up, working in both the Cashmere Basin and in the Peshawar Basin. And Doug carried his research in the Siwaliks forward. He and I and Gary Johnson collaborated on a variety of papers, putting together the synthesis of the Peshawar Plateau, and then Doug, in a series of professorships in various universities, was able to investigate mountain ranges around the world, and placing them into a context based on the research that he'd done in part in Pakistan. He has followed that up with writing many papers on the evolution of structures and their stratigraphic records in a wide variety of mountain ranges. He's put together textbooks on tectonic geomorphology, and he's been a wonderful collaborator across many different institutions. And it's really good for us to be able to bring him back to his roots, maybe here in the Siwaliks. And I want to welcome Doug and give everybody a round of applause and just welcome Doug to the forum. And we'll look forward to his presentation. So, Doug, take it away.
I've opened the share tray.
And as Doug is getting his slides organized, I just want to really stress the fact that I've looked at and I've watched many different people do their research over the years, and Doug has had a marvelous ability to bring together teams of people from China, from Europe, from Asia, and from South America, and other parts of the world, and pull it all together and do it with great sort of camaraderie and a sense of good fun and collaboration. So as his slide sharing is still happening, Doug, I'm giving you a few minutes here to get it to happen.
So my screen, I'm seeing my slide, but you're not yet. Is that right?
Yeah, I think it's coming on.
It'll come up. There's a little delay.
Yeah.
So once you start to see it, we're in good shape. So I think everybody can appreciate that there might be some little bit of lag on the internet, depending on where you are. So Doug, we will, if you speak, we will eventually see. And I think you should just
great popular speeder.
march forward and see what happens.
All right. Okay. So you see my first slide?
I think it's
no. We don't.
We can see you.
Do you see me?
Yeah, we still see you.
That's with me.
Yes.
Okay. Let's see.
I think you need to share it.
I went open share tray. Let me go back there.
Okay.
Let's see.
No, it's working now.
Okay. So, do I close the share tray or I open share tray?
Open share tray.
Yeah.
And then click on the specific presentation.
Yeah.
Okay. So I hit open share. So I'm clicking open share tray, and now I'm clicking on my presentation. I think.
Yes.
It's working. It's working. We're seeing it.
Okay.
We see the orange Tibet.
Okay, and then I should go to the standard big screen view.
Yeah, that'd be good. Right now, we still see your 4 slides on the left.
Maybe it's doing it now.
There you go. Doug, it's perfect right now.
Okay.
Yeah, looks good.
Alrighty. Well, now you can see the title. I haven't changed it. So I'll just start as we look at this impressive elevational data stretching from the northern Indian subcontinent up into the Cashmere Basin and ranges farther to the north of Tibet. So tonight I'm going to just give you a little bit of personal background and then sort of delve into some big picture tectonics scenarios for the collision here, focusing a bit on tectonic and climate interactions, and on climate and topography, with the idea of thinking about how that climate may influence the depositional systems and the sediments that we see preserved. And then we'll look at thinking about how that, with a special focus on the Northwest Himalaya. So, do you see this new slide?
Yes, it's visible.
Okay, so this is a nice Google Earth overview looking down across the arc of the Himalayas and across the Tibetan Plateau and the Cashmere Basin up to the north. You can see all of those, some of these major geographic features indicated here. And I'm going to be focusing primarily in the latter part of the talk on the western part here in the Peshawar Basin and the Cashmere Basin. But first, I was just going to give you a little background. I have an unusual pedigree, I guess, for a geologist, in as much as I did a undergraduate degree in literature with a thesis on Aldous Huxley. And I was an outward bound instructor for about 4 or 5 years, working in various places around the world. And then I decided that maybe I would like to be a teacher, and I thought I'd be a high school teacher of geology. And I was very fortunate that Dartmouth college was willing to admit me there as a so-called special student to do the equivalent of their undergraduate degree in geology, even though I hadn't taken chemistry and physics and other things before that. So I was there for 18 months at Dartmouth and got the equivalent of their degree. No official degree from Dartmouth, but they liked me enough that they invited me back later on. And then I went to the University of Washington, where I worked with Stephen Porter on Little Ice Age glacier advances and response to historical climate change on Mount Rainier. So we're looking at the north side of Mount Rainier here. One of my favorite climate routes went right up that face, but mostly I worked down the toes of the glaciers on the moraines. It's trying to figure out the timing of advances using a combination of lichenometry and tree rings to date the advances, and then reconstructing climatic records from the records that have been kept in various forts along the lowlands of Washington in the 1800s to try to reconstruct climate at the time when these glaciers were advancing and seeing how long it took them to respond to changes in climate, which it turns out with these mountain glaciers was somewhere from 3 to 7 years in most cases. And from there, then I went back to Dartmouth and worked with Gary Johnson and Noy Johnson and focused on Intermontane basins in the Northwest Himalaya for my PhD, which I'm going to talk some about today. I should note that the work in Pakistan was really predicated on this wonderful relationship with Dr. Tara Kelly at the Center of Excellence. And Gary and Noy Johnson had both been working with Dr. Tara Kelly for a number of years before I got it all involved with this. But it sort of provided a wonderful source of both geologic knowledge and logistical expertise that allowed us to undertake fieldwork with a minimum of impediments. Prior to my work, to my knowledge, among this group, most of the previous research had been in the Potwar and the Salt Ranges and the Jhelum Reentrant. And as we were searching around, Gary mentioned that very little had been done in the Intermontane basins bordering the Foreland, and he suggested that I focus on the Cashmere and Peshawar Basin, which is what I ended up doing, and I'll talk about those in a while. Let's see. Okay, so there are those two basins, which I'm sure you all recognize very well. There wasn't a whole lot of literature about the geology of Kashmir. I spent a lot of time trying to dig up stuff. There's one great book written 40 years earlier that had a fair bit of stratigraphic descriptions that included information about this formation known as the Kariwas in Kashmir, which were lacustrine strata primarily that DeTerra and Patterson described in their work. So I knew there'd be some sediments to work with. I should mention that we had fabulous logistical support from the Center of Excellence. In the early years, we had the famous, infamous Kenyan Jeep, which was there, KPK, that we drove around for many years. And then subsequently, a few years later, I bought a Suzuki Jeep, which we used for a number of years. And Javed Khan used to caretake that for me when I was not in the field, which was most of the time. This was the model Jeep we had. It's not exactly the one we had, but there's a funny story about going there with a couple of people when we were going to go up towards past Nanga Parbat to do some research up there, and I had a rack and a big wooden box built to sit on top of it to carry all our gear because we thought we'd be collecting lots of rocks. And partway up the Gilgit River, we went through a nice tunnel and everything seemed fine until just as we were exiting the tunnel, and there was a huge explosion as the box hit the ceiling and was ripped off the top of the car. So that was our inaugural trip with that vehicle. Fortunately, it didn't foretell a lot of subsequent mishaps with it. Anyway, I was also going to mention that, we had this great logistical support in Pakistan and from the Center of Excellence, and we had pretty much completely ad hoc arrangements in Kashmir, where we used local taxis and tried to find a reliable driver. I stayed with families in several villages. I tended to do my own cooking, and it was always quite an interesting time, especially in the evenings, because a lot of people would gather around, and I had my stove and my pot and my food, and they would like to watch everything step by step of the cooking of food that I was doing and what we were wearing. And at some point, and I usually had someone who was there as a field assistant with me, but we sometimes I had to almost start undressing before they decided it was time they could leave and I could go to bed. But there's one of the things that with this younger son who came out in the field with us quite a bit, was very helpful. These are the typical type of spectators that we would see when we were out and a different experience than staying in a formal guest house someplace. Okay, so before looking at the Cashmere and Peshawar basins, I just want to talk about some big picture issues. And first of all, just thinking about the Indo-Asian collision and these large-scale tectonics. Can you see my cursor, by the way, when I swing it around or not? Guess that's a no.
Yes, we can see.
You can see it, okay.
Yes.
Good. So here you can see the Indian subcontinent colliding with the arc of the Himalaya and the sort of what's called escape tectonics, with these blocks off on the east side that are escaping off to the east and southeast, and a whole lot of strike-slip faults within the Tibetan Plateau and farther north that are accommodating some of the collision by extruding blocks towards the east. So I'm interested in thinking about the role and relying on other people's work of climate in shaping origins and resultant depositional systems. And one thing to consider is the fact that the Indian subcontinent moved many thousands of kilometers northward as it collided with Asia, and it was transiting across numerous climatic zones. So, for example, today, in the context today, the lower part of this figure is dominated by the easterlies on average globally, and the upper part is dominated by westerlies. And so we'll think about what the consequences of that are. But let's first start just with some simple large-scale origin climatic models. And this is work from Willett and Beaumont. All of the geometries that you'll see in the subsequent few slides are predicated on the same basic geometry, where some plate from the left is subducting down to the right, and the middle crust, upper crust, and maybe lower crust is being scraped off and thrust upwards here. And then you have some type of denudational forcing that's happening in the mountains, and an erosional flux that comes off of the mountains as a result of whatever it is, whether it's rainfall or glaciers that are causing erosion to take place. And the erosional flux, by the way, obviously doesn't have to be one-sided. You'll get erosion off of both sides of an origin. But there's a competition between building the topography and eroding it. So this is where sort of climate and surface processes come into that. And here's one of their initial models. They call the left side the pro side because that's the direction the plate is coming from and subducting underneath the other plate. And these models are subsequent ones with different amounts of convergence, and the color bars are illustrated up in the strain rate, but red is high strain and dark blue is low strain here. So you can see these symmetrical bands of strain that occur here as you thicken the upper crust in the absence of any erosion. Okay, so you have a collision, but you have rather symmetrical strain and symmetrical topography that results from it. On the other hand, here are two examples where now you've added in what they call wind coming from one side or coming from the opposite side. That's to signify that you're bringing in moisture, which is interacting with topography. And now you can see you get very, very different erosional geometries. So when you're bringing in wind from this side, you have a huge mass up in the top, which is eroded on the left-hand side of the origin. And when the wind comes from the other side and the rain is coming in from the other side, the displacement is completely different. The geometry of the zones of highest strain is completely reversed. So the message is that the direction in which the storms are coming into a mountain range can have potentially a very, very big effect in how the range develops as a tectonic and geographic entity over time. All right. Okay, and I think this is just to suggest that you've got these big contrasts between the two sides. Right. So you could ask which one of these is a better analog for the Indo-Asian collision, and I would argue that probably this is a better analog, given that we're getting most of the moisture coming from the south and out of the equatorial and low latitude oceans and wafting into the Himalayan range. And certainly that's true today. This is the path of the Indian summer monsoon as it sweeps out of the warm waters of the Bay of Bengal and up along the Himalayan front and up towards Pakistan. There's a massive downwind decrease in the moisture content as you go along there. And, you know, it's interesting when we think about sort of climate in this modern context and climate in older contexts and ones up in the Northwest Himalaya. We saw a couple weeks ago when Catherine was speaking, the sort of big vegetational changes which occurred, I think, across the Nagari-Dokpatan boundary. And, you know, you could wonder beyond what was causing that change and how much of it had to do with tectonically driven changes in topography or circulation that affected the local climate. So there's a question, you know, we have northward, the Indian subcontinent going about 50 kilometers per million years farther north over time. We have the development of the Indian monsoon in the mid-Miocene when there was a lot of strengthening. There's argument about the exact timing of that, but there seems to be some agreement on that. We have the rise of mountain ranges that could impede westerlies and cause aridification. And, you know, here, when you think about northwestern Pakistan or the eastern or the western part of the Himalayas, I mean, you have this huge range of mountain belts, many of which have been active and during Miocene times, and ones that and till present, and ones that could be considerable orographic barriers. All right, let's look at a little more close-up detail and think about orographic precipitation, that is to say precipitation which is modulated by topography and the wind direction. So here in this cross-section, north is to the right, south is to the left, the southeast monsoon sweeps up from the left. And, here's data from a network that we set up in central Nepal about 15 years ago, and almost 20 years ago, I guess. We can see that the peak of rainfall is offset 25 kilometers from the highest topography. All right, so it's downwind, it's upwind from the highest topography, and this is a pretty typical phenomenon. When we step back and look at the large-scale rainfall distribution, these are data where it's color-coded by the amount of mean annual rain, from red, less than half a meter, to dark blue or purple being greater than 4 meters. From the Tropical Rainfall Measurement Mission, which we call TRIM, and you can see the big amount of moisture down just north of the Bay of Bengal, and it's sort of gradual waning up towards the northwest as you go along the range front, and clearly big changes as you move up into the Tibetan Plateau or out into northernmost Pakistan or areas farther to the west. Okay, and think about the fact that up here north of 30 degrees, we've got westerlies blowing down to the lower part of this figure. You've got these easterlies or southeasterlies, and when you think about northern Pakistan and what's going to be controlling the rainfall there, you certainly have very few orographic or topographic barriers impeding moisture coming in this direction from the southeast towards the northwest. What impedes it there is just the fact that you have rain out all along here as moisture comes off of the oceans and sweeps up along the front of the range. On the other hand, up here we have all these westerlies, but we have this significant set of mountain ranges which can be blocking those and causing significantly arid, semi-arid conditions in through this area in northern Pakistan. We can amalgamate these data, and there are some interesting aspects of this. Whoops, what happened here? So here we're looking along the length of the range from east to west. That's plotted down here in the bottom. We've stretched out that scale. And what you see in blue are the high mountain elevations. In other words, rainfall above 500 meters elevation. And in red are at the rainfall below 500 meters of elevation. And there's a huge gradient in the low elevation rainfall from east to west. On the other hand, the rainfall in the mountains is except on either end is pretty uniform for 1,000, 1,500, 2,000 kilometers along the range. Here, I can see I got my arrows mixed up. They're pointing to the right thing, and they just didn't come in at the right time. Okay, there we go. There's another interesting aspect when you look at these peaks of high rainfall, because in some places, like over here, you just have a single peak of rainfall. In other places, through here, you have one high peak, and then a second high peak of high rainfall, and along through here. Then you come over here, and you just basically have a single peak, as long as you discount the Shillong Plateau, which is far to the south. So, you can ask, what's the role of a topographic relief? And there's Bodo Buchhagen and he in particular did a very clever study here using the TRIM data, looking at swaths, looking at the relief along them. So averaged relief, which is showing this coming out of the foreland and a gradual increase to up to 5 kilometers in average topography here. And in blue is the rainfall that came on a annual, or I guess this was actually integrating about 5 years worth of trim data, as I recall. And we look at some other swaths, and here's a swath that has some contrasting topography where you have about a 1,500 meter rise and then a long interval of in the sort of lesser Himalayas, and then another big rise in topography. And instead of this one big peak that we saw before with 6 meters of rainfall, you have 2 peaks that are about about 4 meters per year of rainfall in each of those. So and we can see this in multiple swaths along the way. We have this steady rise of topography. You get high rainfall, and note that it's from the highest topography. It's over here. The biggest rainfall is happening more than 100 kilometers away. It's strongly offset from the highest topography. Right? And when you have this stepped topography, then we have these double peaks, and the inner peak it's offset from the highest topography, but by much less, by only a few tens of kilometers, as opposed to well over 100 kilometers in these all these ones that are grouped as type A's. Right. So I'm just briefly going to talk a little bit about flexural loading, creating Foreland Basins, and the mountain loads are causing downward flexure and getting this nice asymmetric subsidence, and then when you get eroding the mountain masses, you get a rebound and erosion that takes place here. And we see 2 different river systems commonly associated with those. When you have big sediment fluxes and you aren't trapping lots of sediment in here because the mountain's going up, you tend to see transverse river systems. Whereas when you have rapid subsidence going on, you're trapping the sediments, and you still have transverse river systems close to the mountains, but the longitudinal systems are far closer to the mountains as well, as opposed to these where the transverse systems are dominant, as in the panel D here. Okay. So, the position of these longitudinal rivers depends both on the rate of tectonic loading or unloading and the sediment flux. And a lot of arid areas typically have lower sediment fluxes. So if we look at an image like this, where we see the whole sort of thickness of sediments in the Foreland Basin, the Indo-Gangetic Foreland Basin, and one sweeping around on the western side of the Suleiman, or the eastern side of the Suleiman Range, see pretty different patterns here. By and large, you see rivers cutting across the Foreland, so ones you could call transverse rivers, and then you have a longitudinal river, which is way out here at the distal edge of the Foreland, and pretty much close to the Indian basement outcrops. Whereas over here, you have these transverse rivers, and then they sweep up right next to the Suleiman Range as the Indus-Sutlej system heads south. And one might wonder why that is, but part of it, even though there's quite a thickness of sediments here, I think is because it's so dry here. There's a relatively modest sediment flux coming out of these ranges, and these rivers aren't pushed away. There's no major sediment push, nor a lot of loading that's happening there that is controlling where the position of the rivers are. All right, so let's turn to the Northwest Himalayas. This is what we'll be talking about the rest of the talk here. There's been a lot of previous work done here. So these are just a compilation of a gazillion magnetostratigraphies. These are some of the ones that I added, and but the ones that they're just a infinite amount of work that went into generating these different stratigraphic and magnetostratigraphic sections and providing that kind of control. I'm going to be looking at these 2 piggyback basins, primarily the Cashmere Basin, just because it's probably a little bit more foreign for many of the Pakistani geologists. But I like to think of these piggyback basins as sort of having a competition between hanging wall uplift, which creates space for sediments to accumulate as you uplift above the bounding thrust systems, and the rate of sediment supply coming off of, say, the greater Himalaya or out of the Pir Panjal or up here out of Kostan, in terms of how they fill these basins. And then there's a third component, which is just the rate of river incision that has to exit from the basin one way or another and cut through these uplifted ranges. And that will also define some of the balance of sediment accumulation within these within the basins. So there's an interesting question about whether these piggyback basins are grading or degrading and why they switch back and forth between those at any given time. And it's often commonly a challenge to distinguish when deformation is happening in among these sediments. And one of the wonderful things you can use in places where there are good exposures are growth strata, or if you have good seismic data. And this little cartoon on the top just illustrates the idea of having a fold forming with a steep forelimb and steady deposition out in the areas of basin that are unaffected by the fold, but then these tapering units as you come onto the fold, they give you evidence that this fold was growing as these sediments were accumulating. And if you have some sort of balance between or disbalance between the rate of uplift of a structure and the rate of accumulation, you can simply get overlap that's occurring all the time. If the uplift is faster than the accumulation, then you're going to get offlap and have unconformities across through here, and you can get any combination of those, and they can change over time in terms of both how the sediments are coming in and how rapidly uplift is occurring. These images are from northern Spain, where there happen to be fantastic exposures, and they really give beautiful examples of these things that are commonly called progressive unconformities, where you're moving from highly overturned beds into less and less and less, and more upright beds, I should say, as you go across big unconformity here into upright beds, and you can see all these wedge-shaped geometries. Those are very telling in terms of thinking about when this, a particular structure was growing and causing these beds to pinch out. So then if you can date those, you can get some time control on these. All right, so we're going to now focus on Kashmir and the Jhelum reentrant. Here's a view, Google Earth view, a little exaggerated topography across the Cashmere Basin looking west. Peaks are up to 6,000 meters high in the Pir Panjal. I never got above about 4,000 meters, I don't think. And there's a moderate climatic gradient across the basin from being wet on the south to drier on the north. This is a map that I produced. Here are the sort of main boundary thrusts, the big suite of thrusts that are bounding the outer edge of the Pir Panjal range. The big speckled dots show Upper Pleistocene, Holocene alluvium. The little finely dotted stuff are the Pleistocene Kariwa strata. So these are these infamous lacustrine beds. And they are what I focused most of my attention on while working there. And there are a whole suite of lakes, which is a beautiful aspect of the Cashmere Basins that sit at the foot of the Himalayas. Here, just for your visual pleasure, is a picture of Dal Lake near Srinagar with a bunch of houseboats where tourists stay from time to time. We had a few nights on one of those at one point. It's interesting to think about then what controls the accumulation here. We have the Jhelum River cutting across here, so it has to compete against the uplift of the Pir Panjal. And there's something that is diagnostic, I guess, about the topography here is that we see all these lakes that are up on the far side, nestled near the foot of the Himalayas, as opposed to somewhere on the other side of this basin. And it's hard to say exactly why that is, but it appears that there's more rapid uplift of the active uplift of the Pir Panjal, and there's a huge flux of sediments of these Kariwa beds, which is being flushed out into the Cashmere Basin and then down out the Jhelum River, that are pushing the depositional systems towards the east-northeast. Right. So I did a bunch of paleomag sections, which are delineated here. I won't go into a lot of detail. These were not like working in the Peshawar Basin, for example, because there's a lot of vegetation. You have to scrounge around the base of the cliffs and dig through the trees and such, but they're pretty good exposures in a number of places, and we were able to build long stratigraphic sections where we could delineate different facies, where we saw all these L's stand for lacustrine, sort of mudstones. Lots of times they had gazillion shells in them and such, and they're braided rivers in places, and a lot of small deltas that were built out into these rivers. Why did I do that? I'm not sure. Anyway, here's the magnetostratigraphy through one particular section. And as in so many places in the work that had been done in the Siwaliks, we can see, zones that are normally magnetized, reversely magnetized, but you don't have a really long sequence here, even though this is one of the longer ones that I worked on. So it's hard to know how this ties into the magnetic timescale, other than the fact that we have all these ashes I point out down here, which allow us to do some fission track dating, and they give us a tie point into the timescale. And it turns out that among those different sections that I showed you, a bunch of these ashes we could actually correlate from one section to the other, even though they were separated by tens of meters. We saw the same succession of ashes over and over again, which was the correlation among all of them across those four sections that I mentioned. You can see even here, I think dozens of points through here, but we don't see any of these, and we think that all of this relates to the upper, the between 2.5 and 3 million years. So synthesizing these data together, we could put together a sort of time stratigraphic record, some of which is calibrated, sort of younger than about 3 million years is calibrated with paleomag. Below here, we don't have any calibration. We just know that there's, very hundreds of meters of conglomerates here, and then the zone at the base of lacustrine mudstone that's disrupted by faulting, and it's hard to know how thick that was originally. But we see what we interpret to be initiation of thrusting, the main boundary thrust, 4 to 5 million years ago, and ponding of those existing fluvial systems, probably structural development of the Jhelum reentrant. Well, actually, we know that was going on at that time. What happened here? Oops, I'm going backwards. That's what's happened. There we go. In the middle here, we see rapid uplift just before 3 million years ago of the northeastern margin. So we saw paleocurrents coming out of the northeast towards the southwest, even though we're up in the Pir Panjal where all the slopes are going the exact opposite direction. And we end up having intervals of coarse clastics that punctuate the lacustrine deposition 2.5 million years ago. We don't really know whether these are climatically related. Probably they are at some level, but we don't have any good, I didn't have any good climate record at that time. And eventually we get an end to the deposition of the youngest stuff that I could find a bit after 700,000 years ago as you go into the Bruins interval, perhaps due to accelerated uplift on the Pir-Panjal, of the Pir-Panjal and rapid slip on the main boundary thrust, but it's just speculation. I don't know of any age constraints we have at that point. Okay, so I'm going to turn quickly to the Peshawar Basin just to look at a couple of sections here from Gari Chandan, and just to point out so these two sections between Gari Chandan and Dog here, and they are, Gari Chandan is sort of dominated by braided river and meandering facies, and once again it's dotted with volcanic ashes, which allow us to correlate between different sections. The Dog section is dominated by conglomerates, both what I interpret as alluvial fans, along with braided rivers, and again we have ashes, which are critical to dating these and allowing us to correlate between the different sections, between the two sections at Gari Chandan and Dog, and looking at this whole coursing upward cycle and westward progression between these sites. It's interesting to think about younger deposition within the Peshawar Basin. There's where the Indus water gap is through the Attock range. And some of you probably know that there was a huge flood in 1841 down the Indus. It was caused by a landslide up by Nanga Parbat, which created a lake that extended up to Gilgit and also up the Indus quite a ways. That landslide dam broke as the lake was overtopped, the landslide, and there was a catastrophic flood down the Indus. It wiped out the army of the Raj near the water gap as water ponded there and flooded a huge area. So it was a pretty catastrophic event at that historical event. And, one might ask, is that sort of a one-off? Is it something that is typical? Do you see other events like that? And I guess we don't really know the answer, but near the village of Piran, I described this set of repetitive graded beds that there are about 60 of them shown here. There's a colluvial layer in between, and interestingly, the beds at the bottom are dipping 10 degrees, and the ones above are just a couple of degrees. So it suggests that there's a significant time interval between these two suites, whether this represents one flood with waters oscillating back and forth and creating grading beds, or whether it represents dozens of such events, I don't know. All right. Okay, let's see. Getting late here. I'm just going to try to synthesize here at the end of from the Patwar or the Peshawar Basin up to Kashmir, and a bunch of stuff from the Jhelum reentrant. So here's a suite of those magnetostratigraphies that many of you know. Here's just an amazing example of the time control that comes from this combination of paleomag with ashes. And so, if you have this pattern of paleomag, you wouldn't know where it was except when you have an ash that you can date. And this set of conglomerates has a few paleomag samples in it, but again, you wouldn't know where it was except when you're able to date the ashes. And then it tells you that you have a very, very narrow time slice between the tilting of these, eroding them up, making these beds vertical, eroding them off and depositing this, less than a few 100,000 years, which is pretty remarkable in my mind. And that sort of time controls allows you to, try to look and track rotations. So here are data out of the Swan syncline. Here's the lake conglomerate. So it's appears to be rotated less than the older sediments down back to 9 million years. So there might be a trend along here. You can see how big the uncertainties are, however, so you can't know for sure, but there certainly is a very rapid rotation between the deposition of the lake conglomerate and the modern part water silt, which is unrotated. Okay, so now we're just going to look at a couple more things down along the axis of the Jhelum reentrant. I like this compilation because it sort of shows the time transgressive position of the gravel front through here, and this is the beauty of having all of these paleomag sections through here, which is where all these black dots are. So you can see the gravel front progressing from north to southwest. We have sediment accumulation rates, and again, we can plot those based on what we have from the paleomag data. So you can see 50 centimeters per 1,000 years. That's, 500 meters per million years, and 400 and 300 as you come farther away. We see the changes in paleocurrents from ones which are flowing to the south-southeast to ones that are flowing towards the southwest. And we see the pattern of subsidence, and the gravel front suggests there's real axis of subsidence, which is guiding the whole fluvial system through this area, approximately where the Jhelum River is today. All right, one other contrast here is just to think about the huge facies differences between the Jhelum reentrant on one side of the Pir Panjal and the Kariwas and the Kashmere Basin on the other, where these are dominantly mudstones, these are dominantly alluvial sandstones, lots of sandstone, siltstone, and conglomerate in there. And they allow, this wonderful temporal data set allows us to make pretty nice syntheses of the data to try to reconstruct the timing of sequential deformation, the shifting back and forth of different active thrusts, the progradation of the conglomeratic system, and just the basic general changes in facies through time. All right, so that's where I'm going to finish. This is my high point, our low point, and I'll exit if I can. Let's see. End of show. Click to exit. Come on. I think maybe I did that.
Well, thank you very much, Doug. That was a beautiful traverse across a lot of ground. Let's see if we have some questions from the audience, and maybe Mukhtar and Irfan, if you can detect any questions, we can pose them for Doug.
Okay, we have
thank you, Mr. Hamish. It's very informative, and we got a lot of knowledge. Thank you so much.
Excuse me, we have Catherine Bailey, so she can ask the question. Then after we will go to that.
Sure. Can you hear me now?
I can hear you.
Great. Thank you. Thanks for a really interesting talk. Doug, I want to go back to maybe the first third of your talk when you're giving the huge overview of the Indian collision with the South Asia, and you imply that there are consequences from the Indian subcontinent traversing through different climate zones on both the nature of the sediment accumulation and also possibly on the regional climate in the Foreland Basin. I'm wondering if you could maybe just talk about that a little further. Are you suggesting that perhaps the late Miocene transition we see from forest to grassland is a consequence of moving through essentially different wind ensembles as the Indian subcontinent is moving northward?
I think that's a possibility that's worth considering. I mean, that was, one of the things that was in my mind. At the same time, the growth of all these ranges to the northwest of the area where, of northern Pakistan, from the Pamirs and all the way up to the Altai ranges, farther, for 2,000 kilometers or so along there, are happening in the Miocene and Pliocene and up to present. And only recently there have been a lot of work. People have been working in Tibet trying to figure out the time and the uplift, and it's only recently that they've and the climate change there, and it's only recently that they've people have been arguing. Look, we have the data to show that a bunch of these ranges have been coming up in the Miocene, and some were very active in the Oligocene, and they've been arguing that there are these sort of teleconnections between the two. So I have no real information on that other than what you can dig out of literature in terms of the timing, but it's something that intrigued me in terms of thinking about the possible causes of these relatively abrupt transitions in the flora and the fauna that followed.
Well, I think it's a very interesting idea, and I'd love to maybe pick your brain a little more about it at a later time. One of the things that's been challenging for us is to try to understand the nature, the timing, and the location of the uplift of some of these ranges with the same kind of temporal resolution that we have for the sediments, which, as you know, is extraordinary. And on the other hand, when I read the tectonics literature, there's usually about a 3 to 5 million year error, often written in qualitative language, around the nature of uplift in this range or that range, and it would be so valuable to know that more precisely.
Yes, I agree completely. It's a real challenge, and I haven't really worked in Pakistan for 30 years or something or other, but I think one of the big things that's happened is the development of a series of low temperature thermochronometers that can allow you to look at rocks cooling below 60 or 70 degrees C. So they're still down a ways, but compared to fission track dating of bedrock and some of these others, they're closer to the surface. And there's some other techniques that people are using now to look at slightly lower lower temperatures as well. But that typically, in my mind, is the approach that is most convincing when you have bedrock samples that you can get cooling ages of, and you know where they came from, etc. And it's very different from having a boulder that ends up someplace and trying to figure out where that came from and what its cooling history was, etc. But it's a big challenge,
right,
in these sedimentary basins.
Well, thank you. Thank you. Great talk.
Do we have any other question? So far.
Yeah, I'll ask a question. Doug, in terms of the overall shape of the Foreland Basin in the western United States, when we look at the basins in front of the severe mountain range, which includes a lot of the Cretaceous interior basins here, people talk about a peripheral bulge. And I'm not sure if you've run into that concept, but I look at the modern sediments accumulating in front of the Himalayas and the Indo-Gangetic Basin, and there's nothing like a peripheral bulge. And I'm just curious if that's something that, if you've encountered that in your studies elsewhere, that might imply sort of a compartmentalization of sediments in the Foreland Basin.
That's an interesting question. I don't have a good answer for that in terms of, or at least I have not observed things where I thought we had the density of sections and such that, or seismic data or whatever else that you could use to try to reconstruct active intrabasinal deformation of the sort that one might associate with flexural wavelengths that are, 100 kilometers or whatever in most of these basins. So I guess flexural bulges make sense. The peripheral bulge makes sense in terms of how crust deforms, but I don't know of ones that have been documented in many of these basins or any of these basins that could be pointed to that cause as opposed to some underlying fault or something or other. As opposed,
Yeah, right. Thank you.
We have a question from Shahid.
Yeah, thanks,
please.
Professor, for the wonderful talk. Could you please shed some light on this concept of the westward shift in the course of Indus River from the Peshawar Plateau to its current day course? And parallel to that, are there any evidences from the Peshawar Basin that this Kabul River, due to the uplift of the Attock ranges, had a course shift toward the north? And the third part of my question is there some role of these Paleozoic hillocks or highs within the Peshawar Basin on the drainage control?
Boy, those are all very good and quite profound questions. And unfortunately, I can't really help solving any of those. I have to tell you that in preparing this talk, I had to go back and dig out these 30-year-old papers or 40-year-old papers that I'd written, and look through the figures and put things together again and try to find decent copies that I could use to make slides from. So it hasn't been on the top of my mind, but those are tough problems to figure out. Paleo geometries, where the main channel was, because we have these, you get a stratigraphic section and it's like the Bible, except that there's another Bible over there a few kilometers away that may tell you something different until you have a real, and I mean, that's one of the beauties of the part water. There's been such a density of studies and so much good time control that quite a few certain levels of uncertainties have been greatly diminished there. And otherwise, we end up telling stories about one or two sections that we correlate together somehow and figure out a sensible way to interpret them, but it's certainly not a unique way. So it's a tough challenge that you're pointing out.
Okay,
so in semi-arid basins where you have intermittent deposition, all this sort of thing, it gets even harder.
Okay, so we have there was Andrew asking, but I think we have a Shah. I don't know.
Yeah.
Shah, can you continue, please?
Yeah. Thanks a lot for your excellent lecture. I actually work in Kashmir. I was a bit, like, for example, the Kashmir Basin was formed by, as we know, that it's a piggyback basin, and I think I agree with that. But what seems to be, because this is the only basin which is really big in northwestern Himalayas, like, apart from the Peshawar in this area, we don't have any other basin which is as big as Kashmir Basin. That's number one question that I want to ask you. The second part of it is, what controls the dimension of it? Like, I do understand that it's parallel to the fault, so therefore we would expect it to be parallel to the the major Himalayan fault. I mean the major boundary fault. But what is the control on the on the northwestern and southeastern side, as well as on the other side? Other side is fine, but at least these two margins are very important. And related to that question, because I feel that you were actually saying that most of the transverse river systems, which are actually in the Himalayas, are basically controlled by erosion. So you got the upliftment and then the rivers cut through it, and that is basically by erosion. But if you look at the Jhelum River, when you're forming a basin, the basin is a deathbed for a river. The river will have lose energy in the basin, and then it actually rides and cuts through, and then comes through the Jhelum area. Don't you think that there is actually a fault which controls it, or there are actually transverse faults which may be taking, playing a critical role for how the rivers are?
So you're suggesting that there's a sort of transverse fault that has weakened the rocks that the Jhelum River is following. I mean, it's certainly possible, but there are an awful lot of rugged bedrock ranges that relatively modest rivers have cut through over the years that you see, and the attritional scouring that happens with grains that are bouncing along riverbeds is significant, and things that geomorphologists do studies of pebbles that they put into mills that swing them around, and they see how they comminute and get smaller and smaller through time, and that's what happens in rivers, and they're pounding on bedrock. So I don't tend to see that as a formidable issue when you have relatively good-sized rivers. And the Jhelum has a pretty good catchment, and the Pir Panjal catches a lot of precipitation, so there's big runoff, and obviously those lakes are sustained there in the Cashmere Basin as well. And there have been lakes there. The whole system was dominated by lakes for 3 million years. When I say the whole system, I mean, I don't have data from all over there, but from what I saw, lakes were a very important part of the stratigraphy there for 3 million years, which suggests there was a lot of water. It also suggests lots of fine-grained sediment, which doesn't do very much abrasion. So, you have to have some tools to cut down through the bedrock, but that would come off of the canyon walls and such.
Okay, thanks. And what about the dimensions of the?
I have no idea.
Okay.
I mean, when you look along strike, and you go to Harital Yangar or out to the Kathmandu Basin, I mean, there are lots of places where there are intermontane basins that are bounded by faults, but they, most of them farther to the east are more closely spaced. So you have a basin there, but it's not a big, broad one the way you have in Kashmir. And I think at least one idea is just that it's the mechanics of the rocks, and were there inherent weaknesses? What was the stratigraphy like, the bedrock stratigraphy, that are exploited by the tectonic pressures and the shortening that's going on? And I don't know the answer to that. It's certainly not something I've paid a lot of attention to.
Okay, thanks a lot.
Sorry.
Thank you.
It's good to have questions that can't be answered, because they'll keep geologists going for a long time.
It's true. I think that was all. We don't have any further questions, Bob. So yeah, there's a question from Hamad. Hamad, go on, please.
Thanks for a great talk. And I think that the data you have provided back in 1996 had really put us into the kind of framework to understand the things. So my question is, how you look about the structure chronology and how you link salt range with the Peshawar Basin. Like when we look at the filling of the strata in the Peshawar Basin around 4 million years or 5 million years, and this is the time when the salt range was active. And when you restore the cross sections in Kohat and Patwar, they are roughly the same dimension. What we have in Peshawar today, when you look at the spatial extents, they are like 60-70 kilometer wide. And when you restore all this shortening, this is 60-70 kilometer. So is there some sort of linkage, one can say that this basin was actually developing back around 10 million years or something, and then actual filling of the strata, what we have, is linked with the salt rain back in the Pliocene. Yeah, thanks.
Well, again, I don't know the answer. The presence, I don't know a lot about salt tectonics, but I know the presence of salt really allows rapid deformation and, under relatively low stresses. So that I think that it is, and well, I think that it's hard to make the same sort of predictions that you might make in more contiguous, uniform solid rocks. But I have to say I haven't thought about that problem with Koat and Peshawar and the Salt Range and the Patwar. And I imagine there's some people on the call here who have actually thought about it more than I have, who might have insights in that, but I can't say I can give any useful perspective on it.
Well, I think, Doug, this has been marvelous, and we've gotten to be late, sort of in the North American time frame.
Yeah.
So I'd like to thank everybody for participating and for your time here.
Yeah, it was wonderful talk. Yeah.
And we've got a talk coming up next week on paleontology. Muhammad Akbar Khan from Lahore will be giving us a talk on paleontology. So we'll be looking at the vertebrate record that has been alluded to by Catherine Badgley in her talk and John Barry earlier. So the framework that Doug has put together here allows the accumulation not only of the sediments but also of the vertebrate fossils, and together that makes up part of the wonderful story of the Siwalik. So I would like to again thank everybody for participating this morning and this evening, and we'll look forward to seeing you all next week. And special thanks again to Doug for his presentation.
All right.
Thank you, everybody.
Night.
Yeah, no, thanks, Doug.
Night.